Sorry for this. I think everyone can read, right?
Yeah.
Okay, perfect. So I will go ahead with more, as I mentioned, technical parts, where we will be talking about low resourceness and multilingual code switching scenarios from other language pairs. The first one will be like Frisian Dutch. There I will be talking about like these three techniques where we try to address low resourceness. So in the Netherlands we have been working on the FAME project for last 3 years, and our aim was to disclose the archives of a local broadcaster from the province of Friesland, and Frisian people is also code switch between Dutch and Frisian, and of course like a spoken document retrieval system you call like such a system. Spoken document retrieval is fine, but the challenge was here the data was code switching data, so we need to build an automatic speech recognition that can handle this problem. But unlike Mandarin English case, Frisian is a low-resource language with only 10 hours of manually annotated speech data. So we had to find some solutions to improve the performance of the ESAT. Luckily, Dutch was doing better with its resources, so you can exploit from the resources of Dutch. That's one way we have tried. And eventually, actually, this project has ended. You see me there in this dusty archive with old-fashioned disks. So everything is now digitalized, and we transcribe them automatically. So the colleagues in the TV channel are pretty happy with the results, I can say. So to improve the recognition performance on a low-resource scenario, we tried 3 things. The first thing is multilingual training. This has been commonly done for also, you don't need really code switching to be low resource. There are languages with low resource but spoken more monolingually. So this multilingual training has been applied to these systems as well. What we did is we tried it on the code switching scenario with some minor modifications. Secondly, we have proposed several semi-supervised acoustic model training techniques for code switching speech. In these approaches, we use the raw data, so the non-transcribed data. Because we have 10 hours of transcribed data, but we have a whole archive there actually that can be used, but with no annotation. So we tried automatically transcribing them and then using them later for the training of our acoustic models. And finally, we tried some other data augmentation, so-called. This is a bit vague. I will come to the details. But in this part, we tried using resources from Dutch, which is high-resourced compared to Frisian, and some other machine learning techniques to improve our models. Let's start with the first approach we have tried, multilingual training. So the main point of this approach is you first train your neural network like on highly resourced languages. Of course, the closer the language, the chances are higher that your low resource language will get a better touch from the additional language. The additional language we used here is English. Luckily, Old Frisian is the closest relative of English. So English and Frisian are not that far linguistically. So what you do, you have two stages. In the first stage, you throw all the data, like English, Dutch, Frisian. And then in the second stage, you use the trained, pre-trained hidden layers, but only do a fine-tuning using the target languages, which are Frisian and Dutch. So this approach, of course, gave us some improvements. So we used this system for the second step, which was automatic annotation of raw broadcast data for semi-supervised acoustic model training, as I have just mentioned. This is a bit of a complicated block diagram, but I will try to make it as readable as possible for you by going through each block one by one. So, so we have like a large amount of, well, in this case it's around 150 hours. It could have been much larger, but at that stage of the research, the data, not all data was digitalized, so it was an ongoing process by then. So we had 150 hours of raw data from the archives, so that's what we have used. So of course, raw data means you have everything: jingles, music, noise, everything. So you just need the relevant speech-only parts. For that purpose, we use, for any pipeline you see in this block diagram, we use speech activity detection. It has to be a robust speech activity detection in the sense that it's not an easy problem to detect speech in broadcast data, because yeah, it can be anything, it can be noisy as well. So most of this work has been done, by the way, in SRI International in California. So we have used their already existing systems, and well, it was very helpful to have all these tools together in one toolkit. So the second approach we used was the speaker diarization. Diarization is, maybe some of you know, speaker diarization is the task of saying who speaks when. So you have no idea, you just have, let's say we have a meeting recording. The aim of a speaker diarization system is to label the speakers. Of course, with pseudo labels. I mean, the aim is not to know the name or something, but to say, okay, speaker 1 speaks here, speaker 2 speaks after speaker 1, and that's the speaker diarization task. So in our pipelines, we use speaker diarization to come up with some speaker IDs, which is useful for training acoustic models later. So this was like the second system. And on top of speaker diarization, we also do speaker linking. Speaker linking is, I think the name says a lot already. It's a rather straightforward step towards improving the quality of the speaker labels assigned by the speaker diarization system. So what we do is we just try to find the same speakers that appear on different recordings. Because speaker diarization you mostly do on a single recording. So you may want to know the same person appearing on multiple recordings. That's the first dimension. But you may also want to identify some of the speakers, because we have little but some amount of data, and we also have speaker labels there. So you may want to identify some of these pseudo speaker IDs using the manually annotated data. So that's also kind of linking. You can also say identification. Finally, of course, we have multiple languages. You need to do some kind of language recognition for the monolingual pipelines. So the first thing we have done is we said, okay, we have one speech segment, and based on the decision of a speaker identification system, of course, we have no information about this segment, so that's the challenge, I should remind. We assign, okay, we have a Dutch speech here or Frisian speech here, and use like monolingual ASR systems for the automatic transcription later on. Also, we applied language diarization. I have just explained the diarization task. Language diarization is exactly the same. You don't hunt for speakers, but you hunt for the language. So you just want to label which language is spoken. So, of course, language diarizations give you more fine resolution with the time compared to language recognition. That's the main difference. And eventually, based on all these, depending on the pipeline, of course, some pipelines have separate languages. Some pipelines have like the bilingual data is never separated. So depending on the pipeline, you either perform ASR using monolingual or bilingual resources to obtain the transcriptions. So this is only the automatic transcription thing. We haven't done anything with the automatically transcribed data. This data is later used with the manually annotated data, like as if it's just some training data to use. And from experimental findings, we can say that when we apply language diarization and speaker diarization, this helps to increase the quality of the automatic transcription. So this was a nice research output, which gave us a large amount of code switching data. Even though there are some errors in the transcriptions, it should be okay. So at least we have more than 10 hours, because with 10 hours you can't really go and use the like hundreds of hours from the other data, because then it's you know, there's a huge imbalance. So now we increased our available code switching training data, and in the last approach, which I call data augmentation, and I said that it's a bit vague, but now I will explain what it actually is. From the acoustic point of view, data augmentation is done by using acoustic data from the high resource language, which is Dutch. So there are, of course, other monolingual Dutch databases existing. These are existing databases. We used like some hundreds of hours of data from these databases, and also from Flemish. Flemish is Belgian Dutch, let's say, spoken in the northern part of Belgium. We also added this data for accent robustness, because I mean, Frisian Dutch is also accented. I mean, it's not like standard Dutch spoken in Frisian. So we also added Flemish Dutch from Belgium to check if it helps with accent robustness. And from the language modeling side, of course, language modeling, you need text. You need some kind of code switching text. But as I said, it's really difficult to find this naturally, let's say. So we tried 3 different ways of generating code switching text. Firstly, we used recurrent neural network models to generate text. There are very funny, or yeah, let's say not funny, but nice examples of this application. So this is like a straightforward way of creating text. Of course, you should train your recurrent neural network on this available small, but yeah, only existing code switching data, and then just create a lot of text. So this is the first way. The second way is to use machine translation. Of course, here you rely mostly on your language models while doing machine translation. And we used very simple models for this part of the work. But this is just an idea, you know, because with Dutch, we also have a lot of spoken text. Spoken text is nice when it comes to use trained language models, you know. It's much better than like newspaper text or anything, because eventually we don't speak like we write. So spoken text is very valuable for developing nice and effective language models. And the last source is, I have just mentioned, we have automatically transcribed raw broadcast data. we can still use the transcriptions of this data to improve our language models. So this was the third way of increasing the code switching text we have. I will also present some ASR results. So to summarize, as you see, we have 4 data components. The first one is the manually annotated data, which is like 11.5 hours, very small. Then automatically transcribed data is like 125 hours from both languages. And finally, we have Dutch and Flemish components, which are like 450 hours and 300 hours. We trained the same acoustic models like I have shown in Mandarin and English. So it's the same architecture. And yeah, we have some development and test set to quantify how well we are doing. With the language model, we have like some monolingual text from both from Frisian and Dutch. And the code switching text, as you see, they are on the order of millions, but the code switching text is only 140,000 words, so it's very small. And yeah, we trained a trigram in this scenario, language model with interpolated kinesrenase smoothing. This is just if you're interested in. And then we generate 50 million words using the first technique here, just using a recurrent neural network. And the second source helps us getting 8.5 million words, which was like the machine translation technique, which is actually the translation of 8.8 million Dutch words, but of course sometimes it doesn't work, so it's a bit less. And 3 million comes from our automatic transcriptions. So we train it like a final language model on this 107 million words. First, I will present some perplexity results. Perplexity is just how we see if a language model is doing a good job or not. And then I will move to automatic speech recognition results. So with only using the data, text data we have, we are around like 257 on the transcriptions of the development data and 231 on the transcriptions of the text data. So I said like adding 50 million generated text using recurrent neural networks helps us actually reducing the perplexity severely, I can say. So on the development data, we end up with 195.2. And so adding the text generated during the automatic transcriptions helps further. And then we end up around 180 on the development set. Well, the machine translation does not really help, it's marginal, but the reason is we should have used more sophisticated language models, so I don't really want to say it will never work, but in our case it didn't give, let's say, any significant improvement. Now what we will do is we will first use the baseline language model and take a look at the ASR results. First adding acoustic data, and then I will also change the language model to this new enriched language model and see if we gain anything on the ASR accuracy. So the baseline system, so only using 11.5 hours, we are at like 37.8, which is higher than the results I have shown. But automatic transcriptions, like thanks to the increased amount of data, it brings with 5% absolute. It's a nice improvement. And then when we add a single copy of the monolingual Dutch and Flemish data, we actually gain. This was not the case before the automatic transcription, because the models were becoming Dutch models only because of so much Dutch data. But now, actually, we get another 5% improvement. And now we are like 27.6% word error rate. When we also apply augmentation and triple the amount of Dutch and Flemish data, we get some marginal improvements, bringing us to 27.1%. And as I mentioned, we used so far only the baseline language model. We can still do like rescoring is a common practice in ESR. Rescoring also helps, and like the lowest results we can get using the baseline language model is like 25.4%. And when you look at this, actually the new enriched language model gives us better results than the rescored results of the baseline. And on top of this, if we do also the rescoring, which is it's a standard block in the ESR pipeline, so we end up with 23.5%. If you check, it's a huge improvement actually, and it's also consistent. As you see, you can see on different utterances, like monolingual utterances, like Frisian, Dutch, and also mixed utterances. So in all subsets of the development and test data, we get improvements. That's also remarkable, because you may improve your Dutch performance while losing from Frisian, then it's not really what you want. But here we gain in all scenarios. So, and this is all thanks to this automatic transcription stage we have taken. Okay, so this was kind of the 3 solutions we have proposed for low resourcefulness, and in the final stage I will be taking you to South Africa. Of course, South Africa has also a very multilingual culture there with 11 official languages. You see here the dominant languages only, but actually languages are they're like just mixed. I mean, all languages. Well, of course, there are dominants in some certain regions, but it's like a big pot of very many languages, and they also code switch, as you can imagine. So with colleagues from Stellenbosch University, we tried to build a 5-lingual code switching ESR system. So you can see this as an extension of what I have been telling so far. So far we have been dealing with 2 languages. But there are, like Singapore is also, I mean, we have 4 official languages, more languages are spoken. What if we try how well actually the modern ESR architectures would perform if you want to build a unified system for, in this scenario, 5 languages. So that was the goal of this study. I will not go into the details of the South African corpus, but it's extracted from soap operas. And of course it's very emotional, you know, speaking rate is faster, and yeah, it's not easy data, I can say. And the amounts, I have marked them in red, so the amounts are also very limited. I think actually this is also a low resource scenario. Maximum amount of data we have is with English, it's Zulu, it's around 5 hours. The least is with Sesotho, English Sesotho. It's like 2.8 hours in total. For this acoustic model, we have been talking about acoustic models already. Of course, here our aim is to capture the acoustic word and phonetic inventory of 5 languages. Also the acoustic information of 5 languages. So what we do is like we train such a system with 5 different softmaxes for each language. Of course, this can be, you can make this more complicated, but this was just an initial effort to build such a system. You may say, okay, if there is, what about data? We have way more data in English, of course, but we use this balanced corpora, which I have just presented, to avoid one language pair dominating the model. So and we did not include any monolingual corpora, which is available. But for this study, we just want to see how well the models are performing. For the language model, we follow the different strategy here. We have the transcriptions of the training data. So what we did was we merged all the code switching data. We tried a 5-lingual code switching language model. That's our first model. And we trained, like, from monolingual, the indigenous languages, the African languages. We trained a 4-lingual language model only from the monolingual text of indigenous languages. And finally, of course, with English, sky is the limit, so a lot of text is available. So we trained a third only English language model, and we interpolated these 3 language models. This strategy gave us the lowest perplexities on the transcriptions of the development data. So this is how we obtained the language models. And finally, some ASR results. I mean, you don't need to bother yourselves, just take a look at the best system, which is around 55.6% word error rate. I mean, this is much worse than what I have been presenting. Given the small amount of data for each language pair, and also being a 5-lingual system, I think this is not a bad start. I must admit that, actually. I was very happy when I first saw these results on my computer screen. But what is more concerning is actually there is a large gap between the English and the mixed African language. So we are doing way better on the English words than the mixed African language. So that's yeah. Of course, each database has English component, so the system has like 4 times more English data than the other languages. This only makes sense, but yeah, this is something we have to address. Also, for example, in the case of Singapore, we have a lot of English data, we have a lot of Mandarin data, but Malay we have less, or like Tamil, other languages spoken here, we may have less data. So this is always an issue, while training such a unified system. And finally, of course, it's an ASR system, but you can also do language recognition, because your words have language tags. So based on these tags, you can also do language recognition. I marked 2 parts with purple and green. Isizulu and Isikosa, same close relatives. So I just marked with purple their confusion, and with green I marked the confusion of other similar languages, Setswana and Sesotho. As you see, the highest confusion takes place between these two languages, and it's even worse on the Setswana and Sesotho because of greater linguistic similarity and fewer acoustic and written resources. I mean, the aim is here to more see how bad it can go, and of course, like linguistic similarity is a potential threat, but we confirm that it's a problem indeed with reporting these results. So, in this line of research, there is a long way to go. I can say that. But the first results are still encouraging. So, okay, I would like to conclude my talk now. So, we have presented multiple code switching systems for various languages spoken in different multilingual countries, including Singapore. Well, Netherlands is not really a multilingual society, but that province of Netherlands is, and South Africa. And we modified the resources of a generic automatic speech recognition system so that it can recognize multiple languages and handle language switches. And also several approaches are described to cope with low resourceness and multilingual code switching scenarios. The future work, of course, a very simple extension will be like this unified framework, applying this unified framework to all Singaporean languages. And finally, of course, we need to investigate the end-to-end models, because they will be there in the coming years. They will stay popular. We should investigate what we can actually do in code switching scenarios rather than monolingual scenarios, and we can exploit what kind of properties of code switching to improve our end-to-end models and hopefully make them their performance similar to conventional models. So let me thank to my colleagues with the English Mandarin. I got a lot of help actually. Without the help of my colleagues from NUS and Nanyang Technological University, I couldn't have presented you these numbers. For the Frisian Dutch part, I also have colleagues from different institutions, universities, also SRI International. They supported me with a research visit. My colleagues there were also supporting our research. And yeah, I would like to acknowledge their contributions as well. And finally, with the South African part, my colleagues in the University of Stellenbosch were very helpful. Last March, I was there collaborating with them, and it was a short month, but we did a lot in a short month, thanks to their hospitality and willingness to collaborate. Here are some references that are, I just added them. There are many other works, of course, but these are the most relevant ones. So if you want to check, I will share the slides after my talk, so you can just refer to these references for technical details of all the systems I have been talking actually. Thank you for your attention. It was a long talk, but I would like to thank you for your interest. And if you have any questions, please feel free to ask.
Anyone got questions?
Sorry, I was just thinking, like, you're saying that there's say for different societies, there are different proportions of data that you can actually use for your different languages.
Exactly.
You're saying that, say for Singapore, for English, so for English, you could have a little bit more higher proportion of data, and Mandarin you've got higher proportion. Mm-hmm. So how would you actually prioritize proportion? I mean, try to have as much as possible equal proportions of data to train, or would you prioritize just using as much of the data you have? That means English could have overwhelmingly a higher proportion of data. Yeah. So which do you prefer?
Well, actually, if you have high resources, you will have the luxury to choose. But for low resources, which is a more of a problem actually with low resources, you don't really have the luxury to choose among, I'm not using that, because I just want to show you this table. As you see, I mean, we are adding like more than 700 hours of Dutch data. I mean, our target language is Frisian, but hoping that, neural networks at this stage helps a lot. Because, even adding like Dutch data here, we were getting huge improvements. Also on the Frisian, less than Dutch component, but still getting improvement on the Frisian component. But the answer to your question is, of course, if you can balance. Now we have, for example, with Mandarin and English, we are also using monolingual data. But there we have the luxury to say, okay, 2,000 hours of English, 2,000 hours of Mandarin. So that's perfect. But on the other case, with the low resources, actually, whatever you have, you try to make use of it. And of course, you should be careful while doing this. Just keep an eye on the performance of the low resource language, like we did here. So adding Dutch data actually point. So here, from this line to this line, the system does not see any new Frisian data. It only sees Dutch and Flemish data, which is like accented, as I mentioned. But thanks to this complementarity, thanks to these shared hidden layers, we are even gaining there. So under these conditions, there is no reason actually not to use resources from the high resource data. Yeah.
Thank you.
Thank you.
I have a question.
Yeah.
So for machine translation, right? So one technique that people do is if they want to get good at, like, for example, English and Italian translation, or rather Italian and French translation. So what they do is, like, they train on English and Italian, and then English on French, so that they learn implicitly the translation from Italian to French. So have you considered, since you have data on Mandarin and English, and then you have data on English and South African languages, is it possible that you train like a network on these two data sets to get better at, like, separating English from other languages?
Exactly, using the high resource language like a bridge. That's definitely a nice thing that can be tried. I mean, what we haven't considered that, but I am pretty sure we will have much more improvements if we do such a smart way. I mean, like either using a high resource language, or even training an end-to-end machine translation system, because they are doing much better than the machine translation was. Well, for us it was just, we had one option, one availability, so we said, okay, simple, just use it. But even just moving to end-to-end, neural machine translation would help. Using like English as a bridge language between low resource languages will definitely give an extra boost to the quality, or to the translation quality. So definitely, it's a nice suggestion. Yeah.
I have a question. So
yeah.
we have done a test on for English speaking only, but simple accent. So the word error rate we able to achieve is around 35%.
Okay.
Versus the publicly available, like Google speech to text, is around 40% error rate.
Yeah.
So but when we get back to read the transcripts, even though we have 35% error rate, the text, the transcript is not understandable, meaning that by only looking the transcript, we cannot get back what the user is actually talking about. So my question is that why the error rate is so high for local accent comparing to American English, and given that the current performance, the error rate is so high, is it possible to build any applications on top of speech to text, but for a simple context?
Yeah. So thank you. First, I also would like to share some experiences. So we have the exact same problem. Thousands of hours of read English speech gives 0% improvement with Singlish component. I mean, doesn't help at all. So the first thing is how much training data you have. That's the first problem to solve. I mean, you need really speech recorded in Singapore. Then there are some efforts now. Recently, we have been working on this national speech corpus. It's accented English from Singapore. That's very, very useful data. So we are running some experiments using this data. But I mean, from our case, the only actually in-domain data is the CME corpus. And you said 35, we are at 28% after so many research, so much research. So it's still not perfect. another thing is also when you go through these errors one by one, you know, there are some also, this is also how a bit you evaluate your system. So because sometimes like it is and it's, like the shorter version. So if you're working with conversational speech, these kind of making the words shorter and that kind of, let's say, sloppiness is out there. And this really doesn't help with the recognition process itself, plus also with the evaluation while you're calculating these numbers. Actually, we have a very high word error rate compared to a monolingual English system, American English. But it's still, when you speak to it properly, I mean, today it was not the most impressive performance of our demo, but my colleague from NTU is I think he has given this demo so many times. He has, you know, they are really bonded well with the demo now. He gives, I mean, it is so readable when you read the output, what he says. Of course, I can only understand the English part, but still, I mean, having like 30% word error rate should not necessarily mean that you cannot understand what is spoken on the other side. That can be also a bit how you calculate the word error rate. So I mean, these remarks I can make. Rather than that, I mean, also language modeling and the local words is another thing to address. Because if you just download CMU English lexicon and try to recognize Singlish with an American pronunciation lexicon, you will already have a lot of out of vocabulary words, because we are in Singapore. Singaporeans have their own words for so different things, their own way of expressing certain things. So also the pronunciation lexicon should be ready for that. What we are using to solve this problem with the pronunciation lexicon is to use G2P models. So what you are using is, you can use grapheme to phoneme models. So you can, like on your Singaporean pronunciation lexicon, you can learn a model to map the grapheme, so the orthography, to phones. And then you can check how many out of vocabulary words you have. And then you can also learn phonetic transcriptions for these out of vocabulary words. So that can also help. So I think I said, I've talked about all three resources. Yeah, if you have any other more specific questions, just let me know.
I think we'll just take one more question. Yeah.
Hey, thanks very much for the talk. I really enjoyed it. Thanks for your time. Question for you. You've in your training sets, you obviously have a spoken component and a textual component, and the classifier you're building is one to the other, right? The translator. Have you considered? Did I understand correctly that you've not done it the other way around? I text to speech.
Text to speech is like speech synthesis.
So the reason I'm raising it was not just as an ad hoc, right? It's that if you built such a translator, you could use it to potentially generate samples the other way around.
Definitely.
We have use it to expand your corpus.
Yes, exactly. I mean, you can, if you want to eventually speak to the machines, the machine should say something back. That's definitely a relevant thing. But in the scope of this work, I only talked in one direction, so from speech to text. But my colleagues are also working on text-to-speech systems. But the thing is, they are a bit different. Let's say it's a different line of research.
So the reason I was raising, I don't know if you saw the paper, the work done by Facebook recently. And essentially they were building non-supervised translation systems. And essentially the trick that they had done was, aside from building word vectors for the component languages and worked out a rotation between the two languages to get a rough translation, they had essentially run translations backwards and forwards. Yeah. Repetitiously to overall enhance the reliability of both by essentially generating poor
Well, there are-
but interesting
yeah.
training corpuses.
There is also an interesting work from Japan, Nara Institute of Technology, where they are trying to imitate the human way of learning speech. So it's called speed chain. So what you are doing is you have one ASR system and one TTS system, and you complete this loop. So the data you create with the TTS system, you train your ASR, and vice versa. So and they have shown some good gains actually by using like the speed chain idea.
That was the question.
Exactly, exactly.
Okay, cool.
So that's
Thank you.
Yeah, that's definitely a direction we are willing to work on. I mean, it will be very useful also for under resources, because you can just create data as much as you want with the TTS. Yeah.
Okay, great. So first thing first is a round of applause for Prof. Emre. And Prof. Emre, I think will still be around later if you got questions. And the other thing is also like to thank AI Singapore for arranging this, sponsoring the venue, and also help us to link up with the speaker. So a round of applause for AI Singapore as well. So thank you very much. We are still arranging for November's meetup, so we'll let you know on Facebook once we have it confirmed. Yep. So thank you very much for spending time here today. So see you soon.